All right, in this section, we're going to finish up chapter 7. Um, so, so we're going to still be constructing an interval, and we're going to base it on some confidence level. 80% confident, 90% confident, based whatever we're told here. The main difference here is we're going to compare two different populations. So we're going to look at the difference between the means between two populations, or the difference between the probabilities between two populations, the probability of success between those, the proportions. And maybe you have a business and you're looking at sales, and you have one location and you have another location, and you want to compare those two. So you're looking at the averages, sales per day between those two, or whatever. You just want to compare two populations of information based on some population parameter. So we're either going to do, compare the means or the proportions. In this section, we're going to assume it's independent. And what that means is that what happens with one doesn't directly affect the other. So like, let's say I had a business and I had different locations. I wouldn't want those locations really close to each other to do this, because if one's doing really well, maybe it's stealing business from another one, and that might be affecting it. Instead, I want to say, like, okay, this location is in this state, and this other location is in that state, and what happens with the sales in this state is probably not affecting the sales in that state, just because of the distance involved. You don't have competing, they're not competing against each other. So we're assuming these two populations are independent of each other. If they were dependent, what that means is you would pair them up. If, like, let's say I was comparing, I owned a business that sold suits. And so I might want to look at how many coats I sell with how many pairs of pants I sell. And, I tend to sell them as a pair, a coat and a pair of pants for a suit. So those two would be tied together and they would be related to each other. That'd be a dependent relationship. Whereas an independent relationship, they don't really have anything else to do with each other. All right, so constructing this confidence interval, it's going to be pretty similar to what we've done before. We're going to start off with assuming we know what the standard deviations of both populations are, which means we're going to use z-values when we're constructing this confidence interval. And what we're going to do is again, we're trying to find the difference. So we're going to subtract the means, figure out what that difference is, and then subtract off the error margin and subtract or add on the error margin. And that will give us the interval that the difference is between these two populations is. Now, the calculation of the error margin, since we have two populations, is a little bit more complicated. You'll notice we still have the z value based on the confidence level. So we're going to be like, hey, I want to be 80% confident or 90% confident or whatever. And again, what you'll do is you'll just look at your table there, or you'll go to that chart in your book, but you'll get your confidence level from there, right? But the multiplier to that is a little different. It's going to have the standard deviation of the first population divided by the sample size of the first population, plus the standard deviation of the second population divided by its sample size. So your sample sizes might not be the same. Maybe from this population we get 100 people, and maybe from this population we only get like 40. So they may not be the same sample sizes, and that's going to affect the width of this interval. Just to be clear, to be safe, we should shoot for 30 sample size for both of these. But if we know that at least, if we know from a population we're drawing from, it is mound shape or normal shaped, then we can go in a smaller group. We can use a smaller sample size than 30. But if we don't know that, we should always shoot for 30 or more, if possible. Bigger than 30, the bigger it is from 30, the better. All right, so let's look at page 413, and we're going to look at question 8. We're only going to look at parts A and B for right now, and then we'll look at more of it as we go along here. So let's do some computation. So consider two independent distributions that are mound shaped. So we can go with sample sizes smaller than 30. A random sample, N1. So we have, let's see, where's my writing? Can't write. What's going on here? Let's reset this. Okay, there we go. N1 is 36. And then from its distribution, we got a sample mean of 15 and a random sample size. So N2 was 40. So even if these weren't mound shaped, we're big enough to normalize this. Okay. So, all right. So for A asks us, check the requirements if these standard deviations are known, what distribution X1 follows, explain. So this is a normal distribution. They're mound shape. The original population. We know sigma 1 and sigma 2. Okay. And the samples are large enough. So we got a lot of bases covered here. We got the mound shape, we got the large enough samples. So we're definitely, and we know these standard deviations, which doesn't affect the normal distribution, but it does reinforce that this normal distribution is going to be okay to use here. Let's see, and we're going to use the z values. All right. Given that the standard deviation for the first one is 3, and the standard deviation for the second one is 4, and we have a confidence level of 95%, we want to construct our confidence interval for this difference in means. All right, so let's start with, we got to calculate our E value. So just a reminder, our new formula looks like the following. Sigma 1 squared over N1 plus sigma 2 squared over N2. And then our confidence. So let's get our Z value. So 95, I can't even read my own handwriting. 95, yes. Wait, yes. 95, that's a 5. 95, so I'm gonna go to my table, my Z's. And 95%, 1.96. 1.96. Square root of 3 squared over its sample size of 36 plus 4 squared over its sample size of 40. And we're going to see what we get when we calculate that. So, right. So 1.96 times the square root of plus divided by 40. And this looks about 1.58. Okay, so that's our margin of error. And to construct our interval, it's going to be the difference between the means, the sample means, minus this margin of error, and then the difference of the means plus the margin of error. Okay, so what's x1 minus x2? x1 minus x2, 15 minus 14 equals 1. So 1 minus 1.58. And 1 plus 1.58. So the difference between our means is somewhere in this range, in this interval here. So somewhere between negative 0.58 and positive 2.58. And it's perfectly fine to get negative numbers here. Since we're finding the difference between these two, it could be that the second one is bigger than the first one. I mean, that didn't happen with our particular samples, but remember, our samples are samples. They're not 100% accurate. So, you know, we can get something between those two. Well, there's just a more likely chance that it would be a positive value, the difference between those. Okay. So A and B. All right. Constructing a confidence interval for this difference when they're not known. So again, whenever you don't know the sigmas, then you're going to use the t values from the t chart. So again, same idea. The formula, we're just going to sub in our t confidence level value and our sample standard deviations here. That's the big difference. Now, this runs into a problem. I have to use the degrees of freedom for calculating my correct t value, but I have two different samples and they may not be the same size. How do I decide what the degrees of freedom are? You always play it safe. That's the goal. You always play it safe. So we take the one, remember on that T chart, the fewer the degrees of freedom as you move up the chart, so fewer degrees of freedom is, the larger the interval. And the larger the interval, the safer it is, because you're covering yourself with more possibilities. So we want to go with a smaller degree of freedom. So we're always going to use the smaller degree of freedom to figure out what this t value is. That's going to give you a bigger t value, which is going to give you a bigger interval, which is going to be safer. So that's what we do. We always pick the one that's going to give us the biggest value, so we get the biggest interval, so it's the safest. That's why we're going to do that. All right, so let's look at C, D, and F, the same problems. All right, so C, check requirements. Suppose that are both unknown, random sample. We know that S1 is 3 and S2 is 4. So now these are the, S1 is 3. These are the sample and not the population standard deviations. What distribution approximates the X1 and X2? So this would be the students' t distribution. Okay. Because we don't know the population standard deviations. What are the degrees of freedom? So I guess I need to put all that other information there. X1 and N1 and X2 and N2. So we have those because we're going to need them for our formulas anyway. So let me find out where those values, I put those up here. Okay, so X1 is 15 and our sample size was 36. And X2 was 14 and our sample size was 40. Okay, so what are the degrees of freedom? Degrees of freedom are one less than the smallest sample size. So 14 minus 1, 13 degrees of freedom. So you always go with the smallest sample size because that'll give you the biggest t value. All right, D. Suppose S1 is 3 and S2 is 4. Find the 95. So again, confidence levels 95% for this difference. So we're going to figure out our confidence value. So again, we're going to go to our T table this time. Table, right? 95 confidence level, 13 degrees of freedom. 95, 13 degrees of freedom. 2.160. 2.160. All right, so let's figure out our new margin of error. 2.160 square root of your first standard deviation. Oops, that's not it. It's 3. I'm getting ahead of myself. 3 squared. That's why I put the 2 there. Its sample size is 36 plus sample size of the second one, 4 squared, and its sample size is 40. And so we're going to put that in our calculator. If you have in your calculator, you can go back. I mean, really all you have to do is just change, since they're using the same values, just change this value in front and then recalculate it. But if you don't know how to do that on your calculator, just retype it all. That's fine. And it looks like it comes out to be about 1.74. 1.74. Again, our difference between x1 and x2 was 1. So we're going to have 1 minus 1.74. Oops, mu. Right? Mu1 minus mu2. 1 plus 1.74. So negative 0.74. This difference is somewhere between there and 2.74. So you'll notice that's a bigger interval. And if I could back up real quick, that's a bigger interval than it was before. I mean, it's not dramatically bigger, but it's bigger. And again, because we're using the t values, those are more widely distributed. So you get a slightly bigger interval because you know less information. The less information you know, the bigger you want to make this interval. All right, so we got that. I don't know, I'm gonna skip E. Oh, yeah, that's just using, we're not gonna worry about that. Using a calculator program, we'll move on to F. Based on your confidence interval you computed, can you be 95% that the mean of the first one is larger than the mean of the second one? Are you 95% sure this first mean is bigger than this? No. At the 95% level, we could get a negative, which would mean the second is bigger. So I can't for certain say that the first one's bigger, not at this level of confidence. I can only say that it's more likely. I mean, there's more numbers bigger than on the positive side than the negative side, but there's still a possibility you could get a negative value, which means the second one would be bigger. So I can't for certain say the first one is bigger. Now, if I created this interval and my numbers were between 2 and say 8, well, then I would definitely know for sure at a 95% level that the first one was bigger because I'm only getting positive values in that interval. But if I'm getting positive or negative values in that interval, I don't know. I don't know which one's bigger. I can't tell, with that level. I'd say they're pretty close, but beyond that, I don't know. All right, let's do 1, 4, 5, 7, and again, skip part E. We're not going to mess with that, those programs there, and then 11. So pause the video, go do that, and then come back. Okay, let's continue on. So now we're moving on to proportions. And proportions, very similar to what we just did. So we're going to construct the intervals. Again, we're going to have a margin of error. The way we're going to calculate that margin of error, again, is going to be, it's a little bit different than what we did in 7.3. You're going to use the probability of success, probability of failure, the first one, divided by its sample size, probability of success, probability of failure of the second one, multiplied together, divided by its sample size, take the square root. And again, we're going to assume we're dealing with a normal distribution as long as we're getting more than 5 successes, more than 5 failures from each of these samples. As long as that's happening, then we're assuming we're dealing with a big enough population that we can normalize it. We can treat it as a normal distribution and use the z values, okay? So other than that, it's very similar to what we just did, okay? So let's look at page 413, number 10. Consider 2 independent binomial experiments. In the first one, we have a trial, 40 trials, and we got 15 successes, okay? And in the second one, we had 60 trials and 60 successes, or sorry, 6 successes. So more than 5 successes, 54 failures on the second one, so more than 5, 15 successes on the first one, that's more than 5. That leaves 25 for failures, again, more than 5, so we can normalize it. Let's go ahead and figure out p hat 1. So again, a reminder how we calculate that is you take the number of successes, divide by the trials, and figure out what that is. 15 divided by 40. So 0.375 is our probability of success, and our p hat 2, that's again 6 divided by 60. That's 10%, so 0.10. All right, so just kind of getting some background information here. So now we're going to start the actual problem here. So check, is it appropriate to use a normal distribution? Yes. More than 5 successes and failures in each group, each sample. Okay. B, find the 95% confidence interval. So here we go. Gonna, so I should, C is 95%. Again, 95%, what's that, 1.96? Yeah. So 1.96 square root. Remember our formula, your probability of success. So 0.375 times your probability of failure. And remember, to get that, you do 1 minus your probability of success. So what's that? 625 over your sample size, 40, plus probability of success on the second one, 10%. Probability of failure would then be 90%, again, the complement. And then over your sample size, which would be 60. Do that calculation. 1.96 square root of okay, so I got 0.168. Okay. And remember, again, these have to be small because we're talking about percentages. And then we're going to do p hat 1 minus p hat 2. Find out the difference between those. So 0.375 minus 0.10, 0.275. So we're going to look at this difference minus the standard error. And this difference plus the standard error. And again, you can get negative values here. That's different than if I was just calculating a proportion, a probability of success. They can't be negative, but this can be. This can, because we're looking at the difference between a negative, again, would just mean the second one was bigger, had a bigger probability of success. So 0.275 minus 0.168. So this difference is somewhere between 0.107 and plus 0.443. Notice both of those are positive. That means the first one, at this level, we are sure the first one's bigger. All right, so let's see. That's probably what C is going to ask us. Kind of running out of space here. C. All right. Based on the confidence interval, can you be 95% confident P1 is more than P2? Yes. there are only positive values in the interval, thus at 95% confidence level, we are sure that P1 is larger, right? So since all of these are positive values in that interval, that would mean that the first one would have to be bigger. If it was negative, all negative values, that would mean the second one would have to be bigger with that confidence level. And then like we saw in the last example from the previous part of the assignment, if it's negative to positive, then we're not sure which one's bigger at that level of confidence. Okay, so go ahead and finish up this section, doing 9 and 17, and that brings us to the end of chapter 7. Computing intervals, estimating values. And then we're going to move on to chapter 8. So see you later. Have a good day.